The title of my talk is Standard Errors for Maximum Likelihood Estimates in Possibly Misspecified Parameter Redundant Models. My name is Richard Golden. I'm a professor at the University of Texas at Dallas. So when we are developing a model, we also often have two choices initially. We can choose between a more flexible model, which has many free parameters, or a more constrained model, which has fewer parameters. The more flexible model has the advantage that it's going to tend to be correctly specified. It's going to tend to fit the data, while the constrained model will tend to be less likely to fit the data. On the other hand, the flexible model will have the disadvantage of the fact that it may exhibit parameter redundancy. This can lead to an overfitting problems, while the constrained model will have less of a parameter redundancy problem and less overfitting. The flexible model also could have challenges associated with identifiability. This can lead to inconsistent parameter estimation and possibly ambiguous semantic interpretation of parameter values relative to the constrained model. In this talk, I want to discuss my investigations looking at the relationships between identifiability, parameter redundancy, and model misspecification. And I'll be working within a maximum likelihood estimation framework. And in maximum likelihood estimation, we look for the parameter values which make the observed data most likely. And this is achieved by finding the parameter values that minimize the negative normalized log likelihood function. And as the sample size gets really large, the negative normalized log likelihood function converges to its expected value. And I'll refer to that as the expected negative normalized log likelihood. And that is interpreted as the cross entropy between the probability model and the data generating process. So what is the goal of parameter estimation when we have model misspecification or possibly model misspecification? We don't want to look for the true parameter values because the true parameter values may not exist. So instead, what we're going to say is we're going to make our goal to find a strict local minimizer, theta star, of the expected negative log likelihood function. And in the special case where the model is correctly specified at that strict local minimizer, then that strict local minimizer will correspond to the true parameter values. In addition, it's well known that the maximum likelihood estimates, which are random variables, have an asymptotic Gaussian distribution with a particular covariance matrix. So when the sample size is large, the maximum likelihood estimates are approximately distributed by a Gaussian distribution with a covariance matrix C star, which we call the robust covariance matrix formula. And that is expressed in terms of these two special matrices, A star and B star, which will play an important role in the following discussion. The A star matrix is based upon the second derivatives of the log likelihood function, and the B star matrix is derived from the first derivatives of the log likelihood function. And the A star matrix and the B star matrix, in the derivation of the asymptotic distribution of the maximum likelihood estimates, are assumed to be positive definite. Now, if the probability model is correctly specified at theta star, then it turns out that A star is equal to B star. So a consequence of this is that if the model is correctly specified, the covariance matrix of the maximum likelihood estimates can be estimated in three different ways, using a robust covariance matrix formula, C star, or by substituting the relation A star equals B star into the formula for C star, we can get the Hessian covariance matrix formula, which is basically A star inverse, or the OPG covariance matrix formula, which is B star inverse. Now, I also want to talk about challenges when the covariance matrix is singular. You may have encountered this in your own experience when you are computing standard errors or confidence intervals, that you might have some confidence intervals which are very narrow and some confidence intervals which are quite wide. And in these cases, you might get a warning from the software package saying, warning, covariance matrix is singular, or warning, the covariance matrix is near singular. So now in this framework, we have three covariance matrices to worry about. The Hessian covariance matrix formula, the OPG covariance matrix formula, and the robust covariance matrix formula, which is derived from the Hessian and OPG covariance matrix formulas. So it turns out that the Hessian matrix A star and the OPG matrix B star have important semantic relationships with the concepts of identifiability and parameter redundancy. So local identifiability means that we have a probability model, which is defined as a collection of probability distributions, and we have a parameter vector whose different values index different elements in the probability model. And if we have a theta star parameter vector, which picks out a particular distribution in the probability model, and there is no other parameter vector which is close to theta star in the parameter space, which picks out that same probability distribution, then we say that theta star is locally identifiable. In this example, theta star is locally identifiable since no theta near theta star specifies the same distribution. But here we have an example where theta star is not locally identifiable, since there exists a parameter vector theta sub 3, which is really close to theta star, but picks out the same probability distribution in the probability model as theta star. It turns out that a sufficient condition for theta star to be locally identifiable is that A star is positive definite. This is not a necessary condition, but it is a sufficient condition. Now let's turn to parameter redundancy. We say a probability model is parameter redundant if we can represent the same set of probability distributions of that probability model with fewer parameters. So in this example, we have a probability model with three distributions, and it's represented by a four-dimensional parameter vector. We can rewrite that probability model in terms of a reparameterization where we're specifying those three distributions but using only a three-dimensional parameter vector. Then we would say that the original probability model defined in terms of the four-dimensional parameter vector is parameter redundant. And it turns out that the B star matrix is checking that the B star matrix is positive definite. If the B star matrix is positive definite, that's a sufficient condition for the probability model to not be parameter redundant near theta star. And also returning to the information matrix equality, if the probability model is correctly specified at theta star, then we have A star equals B star. So therefore, if the model is correctly specified, then the sufficient condition for local identifiability, which is that A star is positive definite, and the sufficient condition for local for the absence of parameter redundancy locally, which is that B star is positive definite, both of these conditions are equivalent. In general, however, they are not equivalent if misspecification is present. So the objective of this talk is to relax the assumption that A star and B star covariance matrix formulas are positive definite. And the big idea is that it might be possible to estimate confidence intervals and standard errors for some, but not all parameter estimates. And towards this end, we introduced the concept of a selection vector. So you can think of a selection vector as a vector of ones and zeros. And what we are going to investigate is the asymptotic distribution of the dot product of the selection vector with the parameter vector. So for example, in the special case where the selection vector had a 1 in its first position and zeros everywhere else, then the dot product of the selection vector and the parameter vector would yield the first element in the parameter vector, theta 1. So suppose A star is possibly not positive definite. But suppose that our selection vector satisfies a special condition called the linear projection condition, which intuitively says that the selection vector S is not distorted when represented in a subspace spanned by A star. And in order to use this linear projection condition, we use the notation A star dagger, which refers to the pseudo-inverse of A star. We also need this positive definiteness condition where we compute a statistic, not a statistic, but a parameter C star S, which is S transpose A star dagger, B star, A star dagger, S, and check to see whether that's positive definite. So if these two conditions hold, the linear projection condition and the positive definiteness condition, then a new theorem is that the S transpose theta is asymptotically Gaussian with mean S transpose theta star and covariance matrix C star S over N. So to investigate this theorem, I took an extraction of this data set by Tatsuka in 1984, which consists of student responses to 536 student responses to arithmetic fraction questions. There were 15 questions. Each question is scored as correct or wrong. Example questions are 2/3 must 2/3 equals what, or 4 3/5 must 3 4/10 is equal to what. And then use these parameters to estimate, use this data set to estimate the parameters of a cognitive diagnostic model. You can think of a cognitive diagnostic model as Bayesian network with some latent variables. So so we have 5 binary latent variables indicating S1, S2, S3, S4, S5, indicating the presence or absence of a skill. S1 is a 1 if the skill 1 is present. And then we have 15 binary variables indicating whether the the student answered the question correctly or not on the exam. And so we might have like an exam question, question 3, which the probability it answers correctly is functionally dependent upon maybe a subset of skills, maybe skills 1 and 2. And then we treat the skills as latent variables. So when we compute the likelihood function, we have to integrate out over the possible values of the scale latent variables to compute our likelihood function. Again, there's 2 parameters for each of the questions. So we have a 30 parameter model. And so in the simulation study, we sample with replacement from the original data set of 536 records to generate a bunch of other data sets. So we might sample with replacement 32 times to generate a data set of 32 records, then repeat that again to get another data set of 32 records. And this way we can end up with 200 data sets of 32 records, 200 data sets of 536 records, and so on. Then what we're going to do, if you have like a collection of data sets, we'll estimate the 95% confidence interval for each of the parameter values for each of the bootstrap samples. And then we'll average these confidence intervals across all of the bootstrap samples. And then we'll count the percentage of times that a confidence interval does not contain a estimated parameter value. And that should be close to 5% if our asymptotic theory is correct. If it's less than 5% or more than 5%, that's a deviation from our theory. So we call that the no test condition. We also have the pass condition, where we're only going to use the bootstrap samples which pass the conditions that we mentioned earlier, which were the linear projection condition and the positive definiteness condition. And as you can see, the new method, which is the blue square, works extremely well. It's very close to the target 0.05 level, unlike the other methods, which all get really close to 0.05 for larger sample sizes. But by using this method, we actually get really close to really good confidence intervals for really small sample sizes, because we're compensating for the lack of identifiability and the presence of parameter redundancy for those smaller sample sizes. So in summary, I've presented a new methodology for computing standard errors and confidence intervals when the covariance matrix is singular or non-singular. Got new theorems for showing the methodology works, and new simulation studies investigating large sample approximations of the methodology for cognitive diagnostic modeling.